All right, welcome everybody. Today we're going to talk about lesson number 49. This is another day of using the fundamental theorem of calculus and then directly how it applies to finding the area. Before we get into that, I just want to reiterate the important distinction between an indefinite integral versus a definite integral. So over here on the left-hand side, the indefinite integral denotes a family of functions, each of which is an antiderivative of f. So that means that there are infinitely many answers. This is what we started with at the beginning of the unit. Notice that in your notation here, there are no numbers. So it's indefinite because you don't know where you're starting and you don't know where you're ending. Again, there are infinitely many answers. We call that a family of functions. And the way that we denote that is by ensuring that every answer ends with a plus c. Then, on the other hand, you have a definite integral. Remember that a definite integral starts at some value a and ends at some value b, and the answer to a definite integral is always a number. We talked about how a definite integral can give you a value that is positive, negative, or zero, and that's what we've been practicing for the past couple of days. So now we want to just drill down a little bit more in terms of how do you actually interpret that value that you get as a result of finding a definite integral. So, kind of the important thing for today's lesson is for a definite integral to be interpreted as the total area between the curve and the x-axis, the function has to be continuous and totally non-negative on the interval from a to b. So again, read that carefully just to make sure you understand what it says. If you want the answer to be the total area bounded by the curve and the x-axis, it has to be continuous, which means no breaks, and it has to be entirely positive. The other day when we were starting with the graphical piece of this, I emphasized that each of the problems we had you do was an entirely positive region. That will not be the case going forward. Obviously, in yesterday's lesson and yesterday's homework, you got answers that were 0 or negative, and now we just want to make sure we understand what that represents graphically speaking. So here, theorem 4.5, this is just kind of a summary of what we just said. If you want to interpret the definite integral as the area of a region, again, it has to be continuous and non-negative on some interval. Then the area will always be equal to the definite integral. Then just a little note here for a vocab. So the bottom number, a, wherever you're starting, that is generally called the lower limit of integration, where the other number, b, where you end, is called the upper limit of integration. I think I've been using those words, but here is just kind of the formal introduction of them. So to see this in action, you're going to look at the two examples over here on the right-hand side. Both of these are examples where the definite integral is the total area. So here at the one at the top, you're finding the definite integral from 0 to 2 between that red curve and the x-axis. Because it is continuous and entirely positive, whatever answer you get algebraically will represent the total area. Same thing down here. If you're going from A to B, doesn't matter that you're not starting at 0, doesn't matter where you start and where you end, as long as the function is continuous and as long as it's entirely positive. So again, in both of these examples on the right, if you were to have the equation and calculate the definite integral, you would get a positive answer, which would represent the total area. So what is it going to look like if it's not the total area? Well, let's take a look here at this example. So here, the integral is not the total area, but it's only the net positive or the net negative. So if you look here, remember, whenever you're talking about area, you're talking about the region between the curve and the x-axis. So from A to C, that region happens to be below the x-axis. So that means you're going to get a negative answer for that region. Then if you were to calculate from C to B, that would give you a positive answer. So algebraically, if you were to add a positive to a negative, you're going to get an answer that represents the larger piece. So because the blue positive region is larger than the orange negative region, this area, this answer that you find is going to only represent the net positive area because some of the orange will take away some of the blue. Now, for the problems we're going to do today, we're fine with that. We actually want to interpret it as either the total area entirely negative or net positive or net negative. There will come a time where it's not going to be okay that this is negative, and we're going to want to turn it positive. That will come later in the unit. But for now, we just want to make sure we can interpret, is it all positive, all negative, or some combination of the two? So take a look here at number one. Number one asks you to find the area of the region bounded by the x-axis, the graph of x squared minus 1, and you're doing it from 1 to 2. So we might ask you to graph something, or we might give it to you. In this case, we graphed it for you, and we told you that it was the equation x squared minus 1. Now notice that we're saying that we're doing it from 1 to 2, so that those are your bounds, and those are going to be your lower limit of integration and your upper limit of integration. In a case like this, the first thing you might want to notice is that this region is entirely positive, so that's good to know. Something else you just might want to point out here, so this is the point 1 comma 0, and this is the point 2 comma 3. While we really only care about the x's for integration purposes, if you were asked to graph this on your own, you just might want to be able to find those points so that you could accurately produce that graph. So never a bad idea to kind of review that. If we're going to find the area of that region, again, notice that because it's a curve, there are no shapes that I can draw that are going to give me the exact area. So I'm going to have to use a definite integral, and I'm going to have to go ahead and set one up here. So I'm going to find the integration from 1 to 2 of x squared minus 1, and then don't forget your variable of integration. You're going to go ahead and integrate, so x squared is going to become x to the third over 3 minus x. Remember to draw that vertical line and then say, where are you evaluating it? So you're evaluating it from 1 to 2. And then you're going to go ahead and plug each piece in. So starting with the 2, everywhere there's an x, you're going to go ahead and put a 2. So that is going to give you 2 cubed, which is 8 thirds minus 2. Then remember, it's always a subtraction. Then you're going to plug in the 1, which is going to be 1 third minus 1. At this point, however you're going to calculate it is up to you. You can do each parenthesis separately and then subtract them. You can use your calculator very carefully. Either way would be fine. Personally, for me, when I look at this, I see 8 thirds minus 1 third, and my brain goes to, okay, well, that's 7 thirds. Then I see negative 2 minus negative 1, and that makes me think negative 1. And then when I see 7 thirds minus 1, that makes me think of 7 thirds minus 3 thirds, which is how the answer turns out to be 4 thirds. And again, that is not the only way of thinking about it. That's just how my brain sees it. So you could, again, do each parenthesis separately and then combine them, or simply use a calculator. Remember, a decimal equivalent would be fine as well, but 4 thirds, again, it's a little fancier if you leave it as a fraction, and sometimes the fewer maneuvers you do in the calculator just winds up leading to less user error. But if you did find that, that would be, of course, 1.33. And again, just the thing that I want to point out here is because of the fact that this region was entirely positive, what you have here is, in fact, the total area because it's positive and positive only. Let's compare that here to number 2. So in number 2, notice that they have actually set up the integral for you. So they're telling you to find the integration from 0 to 1 of 4t plus 1 squared dt. So notice that in this case, you're using the variable t instead of x. No real difference, but maybe worth pointing out. Something else maybe to consider, this is the point 0 comma 1, which I get by plugging 0 into this equation. This is the point 1 comma 25, which again I get by plugging 1 into this equation. And that would be helpful if you didn't have the graph in front of you to help make sure what you had was accurate. Something you want to note here is that, yet again, you have an entirely positive region, which means that you know that the answer you get should not only be positive, but it will represent the total area. So even though they have set up the integration for you here, currently it is not in a form that I like. So I'm going to go ahead and actually do that FOIL. Remember, there are no integration rules that undo chain rules or products or quotients. There won't be still for a couple of days or maybe even weeks. So I'm just going to go ahead and rewrite this as the integration from 0 to 1. If I go ahead and do that FOIL, I'm going to get 16t squared plus 8t plus 1, and then don't lose your dt. So I'm going to go ahead and integrate now. So 16t cubed over 3 plus 8t squared over t is just going to be 4t squared. And then don't forget the t. And I'm going to evaluate that from 0 to 1. Anytime you wind up having one of your bounds being 0, it's just kind of nice because it's a simple calculation. Don't disregard it completely, but it is just going to give you an easier calculation. So start by plugging a 1 in for every t. So that's going to give me 16 thirds plus 4 plus 1. Then remember, it's always a minus. And when you plug in the 0, you're just going to happen to get 0. So this here is 16 thirds plus 5. I'm going to go ahead and change that 5 to 15 thirds, which is going to go ahead and give me a total area of 31 thirds. And again, if you wanted to make that a decimal, that would be fine. It would be 10.33 repeating. And again, because of the fact that I can see the picture and I can see that it's all positive, that is how I know without a doubt that this is the total area of the region in question. So now, obviously, there'd be no point of doing this lesson if it was not always the total area. So let's go ahead and see some examples on where it isn't. All right, so notice on the back here, we have a single function, negative 2x plus 3, but we have 4 different versions. While the picture of the graph is obviously the same every time, we are given different values for which to evaluate the definite integral. So not only do we want to think about what those different values would look like algebraically, we also want to think about what they would represent in terms of the shaded region and the area. So just so you know, I had tried to do those pictures in real time as I went through, but it was kind of wind up being too messy. So I went ahead and did them all ahead of time, but you should add them in as we go. One other thing you might just want to jot down, we're going to be using also some of our old geometric formulas for area, and you're also going to need those for tonight. So if you just wanted to give yourself a quick reminder, the area of a rectangle is, of course, length times width. The area of a triangle is 1/2 base times height. And then the area of a trapezoid is equal to 1/2 the height times base 1 plus base 2. So again, you might just want to jot those down so that you have easy access to them, not only for the rest of today's lesson, but also for tonight. So keeping that in mind, let's go ahead and take a look here at number 3, the first one. We are talking about the definite integral from negative 2 to 1 of the function negative 2x plus 3. So again, you should shade and highlight the region that I have here, and then let's talk about what that means. So again, in terms of how I got these points, negative 2, 7, if I plug negative 2 into the equation, I get 7. If I plug 1 into the equation, I get 1. And that's worth knowing just in terms of the shape part of it. So I'm going to go ahead and first find the algebra using the formula of a trapezoid, which this is. If you turn your head to the right or to the left, you should see those parallel bases. So to find the area of a trapezoid, it's 1/2 times the height. So the height of the trapezoid would be here, again, if you turn your head, and that's 3 units in length. Then base 1, which is from 0 to 7, plus base 2, which is from 0 to 1. So if you go ahead and calculate that, 7 plus 1 is 8, 8 times 3 is 24, and half of 24 is 12. That tells us that the area of that region is positive 12, and when I do my definite integral, it should, of course, agree. So if I go to integrate, I'm going to integrate negative 2x as negative 2x squared over 2. That would, of course, just become negative x squared plus 3x. And just so you know, you are going to use that same integration for each problem because it's the same function throughout. It will not change. And then you're going to go ahead and evaluate that from negative 2 to 1. So starting with the upper bound, which is 1, you're going to get negative 1 plus 3. Then remember, it's always a minus. If you square negative 2, you get positive 4, but then you have to make it negative. Minus 6. If you do the first parentheses, you get 2. If you do the second parentheses, you get negative 10. And then 2 minus negative 10 becomes 2 plus 10, which again gives you a final answer of 12. And here, this is the total positive area, all between the x-axis and the curve, and again, all positive. And again, the answer you get algebraically should also be the answer that you get over here using the geometric formula. Let's go ahead and take a look at the next one to the right, number 4. So here you're finding the integration from 2 to 5. So again, notice that I started at 2 and I ended at 5. I got those points 2, -1 and 5, -7 by plugging them into the curve. Again, if you want to have the geometric component, we would go ahead and find the area of the trapezoid using the same formula. So 1/2. The height of this trapezoid would again be 3 units. Base 1 would be from 0 to -1, so that would be -1. Then from 0 to -7 would be -7. So -8 times 3 is -24, half of which is -12. So it should make sense that you're getting a negative answer because you are all below the x-axis. So if you, again, go ahead and integrate, you're going to get the same value of -x² plus 3x. That will not change, but now you're evaluating from 2 to 5. So starting by plugging in 5, you're going to get -25 plus 15. Then always a minus, -4 plus 6. That's going to give you -10 minus 2. And -10 minus 2 is, of course, -12. The two answers should agree, and this is basically the total negative area. Now, again, can area actually be negative? We're going to dive more into that as the lessons progress, but for now, we are trying to interpret it as all positive, all negative, or net positive and net negative. You probably get the idea, but doesn't hurt to just kind of show it. Take a look at these last two examples. Here, you have some positive and you have some negative. So your final representation is going to represent the combination of the two. If you take a look at number 5, you are going from -1 to 4. So again, notice that I have found those corresponding y values just so I can make it easier. When you go ahead and find this calculation for the area, you should actually do the two separate shapes. You, of course, have two different triangles. So if you're going to find this area, you're going to start with the area of the first triangle. So that would be 1/2 the base, which is a distance of 2.5, times the height, which is a value of 5. So again, this is the base from -1 to 1.5, and I know that that's 1.5, 0. That is the x-intercept of the function. And then I would have to add that area to the blue. So the area of the blue triangle, let me just color code that for you. So that is the yellow. And then now if I do the blue, this is going to be 1/2. The base is from 1.5 to 4, so that's 1.5. Then the height would be from 0 to -5, which would be -5. And that's going to be the blue region. So if you go ahead and calculate each of those areas, the yellow, so 1/2, 2.5 times 5, that is 6.25. If you calculate the blue, 1/2 of... and sorry, that should be a 2.5 there. The distance from 1.5 to 4. Yep, okay. The distance there is going to be -6.25. And when you look at that, it turns out that it cancels out to be 0, which, again, if you look at it, graphically speaking, should make sense because the area of the yellow is exactly equal to the area of the blue. So it should make sense that they should cancel out. And then let's just go ahead and make sure that it does so algebraically. So when we're talking about the algebra, again, it's always going to integrate the same way. So -x² plus 3x. You're going to evaluate it from -1 to 4. So if you start by plugging in 4, you're going to get -16 plus 12 minus, if you plug in -1, first you have to square it and it becomes a positive, then make it negative, -3. That's going to give you a -4 minus a -4, which of course does cancel out to be 0. So the net positive area and the net negative area cancels out to be 0 exactly. So perfectly fine for that to happen algebraically. We've actually already seen it happen algebraically. Now we just want to understand the graphical component. And then taking a look here at number 6, even without doing any calculations, it should make sense that your final answer is going to wind up being negative because the area of the blue triangle is larger than the area of the yellow triangle. But let's just, again, confirm that. So in terms of the area, if I go ahead and start by doing the area of the yellow, it's going to be 1/2. the base, which again, this is 1.5 comma 0, is 1.5 times the height, which is 3, plus 1/2. The base of that triangle is 3.5, so the distance from 1.5 to 5. And then the height, because it's going in the negative direction, would be -7. If you go ahead and combine those two things, you're going to get an answer of -10. So let's go ahead and do the final algebraic step. So that's going to give me -x² plus 3x. Again, it's the same integration every time, and I'm going to go ahead and do that from 0 to 5. Starting with the 5, I'm going to get a -25 plus 15 minus, and then because it's a 0, I'm just going to get a 0, which is going to give me a -10. And again, what this represents is the net negative area, because of the fact that some of the yellow canceled out some of the blue. So it's not a total negative area, it's not a total positive area, but it's the net negative area. So again, hopefully seeing that same problem 4 different ways, where you have a total positive, a total negative, a total cancellation, and then just the net negative. I could have shown you the 5th version where it was a net positive, but I figured at this point you would get the idea. So I don't think anything we did today was particularly difficult, but it is important that you're able to do problems of the sort. So I just actually want to pull up homework 49 really quickly, just to kind of explain a couple things. Here for number 1, notice that there is no equation. That is on purpose. We don't want you to find the equation. All we want you to do is to calculate each of those indefinite integrals. We want you to understand that it comes by just finding the area of the shapes. So find the area using the geometric shapes. So draw rectangles or trapezoids or triangles and find each of the areas just using those shapes, and keeping in mind they could be positive or negative. And then whatever you get for those geometric shapes would be equal to what you got if you did the integration, but we're not going to have to actually ask you to do that since you don't have any equations. Here for number 2 and 3, we have the picture for you. It shows the shaded region and it shows the equation. You're going to set up and solve the definite integral. Then for the final 3, again, we have the graph for you and we have the integration. You're going to not only find the definite integral, but then you're also going to shade the corresponding region. So the truth is, if you're able to do homework 49 here, it shows that you have a perfect understanding of both the fundamental theorem of calculus and its graphical relationship. So thanks very much for tuning in, guys, and we will catch you next time.